Well,
Okay.
welcome back. Let's now listen to Phil on spectral timing with EXTP, the view from now to the future. Thank you.
Thanks a lot. Yeah, great to be here and talking to you remotely. So yeah, I'm going to sort of give an overview really of spectral timing, specifically with EXTP, focusing on the black holes. And the idea is really that, you know, right now we're sort of looking at a time. I mean, I think it's an amazing time actually to be doing this kind of work because of missions such as NICER, and of course the heritage we've had from RxTE, and then looking forward to these great missions in the future. But it's quite a good time to look at what, you know, where we've come and what recent developments have been, especially from NICER, and how that impacts on what we're going to do with EXTP. Okay, so you know, the basic problem that we have, right, is you know, when we're studying black hole X-ray binaries, is that these innermost regions, obviously we can't image them. And so traditionally, you know, you can take an X-ray spectrum, for example, or do a timing study. But if you look at the X-ray spectrum, we can see a few spectral components, such as the black body emission coming from the accretion disk. I mean, this is an example of a hard state spectrum from GX339-4. And of course, you get the reflection spectrum as well. But then you have this mysterious power law emission, which we kind of call the sort of component contributing that the corona. And a good argument I heard from Javier Garcia was that that's because it's above the disk, right? So we know, the only thing we know for sure is it has some sort of vertical height relative to the disk because it produces reflection. And, you know, of course, we can consider different models for that because we don't have that much information from the power law about the scale at all if we just look at the spectrum, unlike the case with the black body and the reflection, where we have some idea of the scale from the spectral shape or the temperature. So, you know, you can come up with various models for the structure of that corona being a large sort of extended region, more compact, perhaps a sort of inner hot accretion flow, or even the base of the jet or the jet itself. And this is still being debated. And part of the problem is that we don't have, you know, we don't have this information from the spectra alone. It's very degenerate if we fit spectral models. And what we need to have is some sort of causal information, which we get from the timing. And so we can combine the spectrum and the timing, and we come up with these spectral timing techniques, which we've been using already for many years. So just to remind you, I realize I think we didn't really have an overview yet of the EXTP's payload, and maybe some of you are not so familiar with the EXTP. So the key points are that you have on the mission, this is I think the design has changed a little bit since this was sort of the previous iteration. And I think now these large detectors here that look like solar panels are actually the large area detectors. And now they're fitted, I think, more, maybe not as separate panels, but around the sort of, on the spacecraft body itself. But basically, these are that contribute this large contribution at the effective area in harder X-rays, so above a few keV. These large area silicon drift detectors. So they're kind of like the proportional counters of the future. You know, NICER has pioneered this kind of technology for X-ray timing. And, you know, so we can get CCD type resolution, soft X-ray, softish X-ray response, but in particular large areas. And then if you look in the center here, you have these focusing optics instruments, and in particular the spectroscopic focusing array, which is this red curve. And so that gives us even softer X-ray coverage. So this is giving us something like 4 times the collecting area of NICER at 1 keV, and goes significantly below the LAD, below a keV. So that turns out to be really important with what we've learned from NICER. There's also the polarimetry focusing array, which is this smaller effective area here, but it's still, I think, 4 times the effective area of IXP. So that's also going to make some breakthroughs there for sure, but I'm not going to be talking about the polarimetry. And of course, the wide field monitor, to finish it off, is a thing that tells us what's going on in the sky at any one time. So the case has been made. I mean, in particular, if you're interested in looking at the details, look for the EXTP strong field gravity white paper that was published a couple of years ago. And so these are some the key examples related to spectra and timing. And the ones on the left, this is timing high frequency QPOs and timing polarimetry. I'm not really going to talk about, but you can go to the white paper for those. And I'm just going to focus on the pure sort of spectral timing that uses the energy information as well as the timing information. So in particular, that's going to be the phase resolved spectroscopy of QPOs. That's something that we've already started doing with RxTE data, and now it's being worked on with NICER, also XMM Newton as well. and the reverberation lags, which is kind of a hot topic at the moment. And there's a lot of results on this coming from NICER, so I'll talk about that in some detail. So this is the idea of measuring light travel time delays between the corona and the disk by looking at the time lags, in particular in the reflection signature and in the reprocessed soft X-ray emission as well. Okay, so Tom kind of anticipated this as well by talking about the role of GINGO, which was of course very important. I'd also mention EXOSAT as well, but actually if you look at the first, so specifically focus on spectral timing measurements, the first real spectral timing using Fourier techniques like the cross spectrum to measure the relationships between different energy bands as a function of time scale or Fourier frequency. That was done by EXOSAT by Michiel van der Klis, and actually the GINGO work done by Miyamoto et al. Was motivated by, they actually say that in their paper, by the work by van der Klis on EXOSAT data. So those were really the first two instruments to really pioneer these techniques. Of course, RxDE contributed with its high count rates and especially its flexibility. That was especially where I think it had an advantage over GINGO, operating for a long time, but excellent scheduling, very good pointing flexibility, rapid response to new targets. And that revealed a really rich phenomenology because of its flexibility, that you could observe and see these state transitions in detail and see all these complex phenomena that we're still talking about and interested in today, like the type B QPOs that we already heard about from Holger. Now, in 2008, now XMM Newton was launched in 2000, but I think it was about 8 years later that we really started realizing we could do this do spectral timing on X-ray binaries with XMM Newton. And so that was giving us the opportunity to look at soft X-rays for the first time with higher spectral resolution from CCD instruments as well. But of course, the limitation with XMM Newton is that it's limited in count rate. It's limited mostly, I think, by pilot, but also by the telemetry, right? How many counts the instrument can collect and send down. And so you're limited to maybe like 1,000 counts a second, something like that. And then you have quite a bit of pileup as well, but you can do spectral timing with that. And so you can do reasonable spectral timing studies, for example, GX339-4, Cygnus X1, but in the hard states when the source isn't too bright. So we weren't able to see what was happening in soft X-rays in the interesting state transitions which happen at higher luminosities. And so we had to wait till just a few years ago for the launch of NICER to be able to see this in effectively RxC count rates in soft X-rays. But with really great resolution comparable to XMM Newton, CCD resolution now, and unlike instead of proportional counter resolution that you had with RxCE. So you're approaching something like 150 EV resolution at the iron line, for example. And at the same time as NICER was launched, very close actually in the summer 2017, Insight HXMT was also launched. That's important for two reasons. First of all, the high energy coverage. I'll focus on the soft X-rays. But there's been some very interesting timing results, for example, detecting low frequency QPOs up to 200 keV at hard X-ray soft gamma rays. And I think that's going to be very important, perhaps, for understanding the role of the jet, if that plays some significant contribution at those much higher energies. And of course, also because EXTP being a Chinese mission, I think Insight HXMT is really demonstrating, sign of setting the scene for the launch of EXTP by building up this experience at operating a major X-ray observatory. And of course, we're here now, and so we have a few years of experience with these instruments to be able to think about EXTP. Of course, coming up, we have XPay, so that's going to give us our first window into polarimetry. Now, it's not really a timing instrument as such. It's not got a large collecting area, but you could imagine teaming it up with NICER, for example, to get large count rates, and then doing a kind of cross-spectral analysis to do maybe timing polarimetry. So I think that would be a very interesting thing to do with XPay in the coming years when you have new sources or bright persistent sources. And of course, in 2027, we're waiting for EXTP. And so what we want to think about is what have we learned so far, and does that affect any of the science that we might want to do with EXTP? And in particular, I'd want to point out that EXTP, the concept, it kind of derived from this original XTP concept plus the LOFT mission, which was proposed for the European ESA M3 selection, and narrowly missed out on that. And so EXTP, since I don't know, about 8 years, something like that, has been, been put together. So originally, we didn't really know anything about the results. Like everything we know from NICER has happened since the original science case was formulated for EXTP. And what I'll show is that actually we don't really need to change too much. Fortunately, we were conservative enough with our simulations that some of the new results from NICER don't really change things. Okay, so starting with RxTE, and this is what really set the scene in terms of phenomenology and understanding what was out there in terms of spectral timing and lags. In particular, just measuring time lags, of course, the limitation of RxTE is the energy range, right? So you're sensitive really above 3 keV. And so when you're looking at the hard states, at least, you're really seeing the power law emission, right? You're not seeing the disk contribution at all, except it may be in reflection. And so, these various results, for example, these work by Kaciopod-Schmidt back in 2000, which showed that in the different states in Cygnus X1, so not quite like the sort of state transitions that you see in transients, but with these sort of so-called failed state transitions. And of course, the soft states exist in Sig X1. They look a bit different, but they also seem to correspond to the jet getting relatively quenched, although it's still present in the soft states. So similar phenomenology, but it actually, if you look in the hard states in transients, they show similar lags. And so you see basically that you have hard lags, so higher energy photons in the power law lag the softer energy photons, lower energies. And in particular, also that the lags depend on the Fourier frequency. So depending on the state, if you're in the transition, it's relatively flat with a kind of constant lag versus frequency. But in the regular hard states, the lag decreases with frequency. And you have kind of some structure as well, some sort of steps in the lags as well that may correspond to the changes between these different Lorentzian components in the power spectrum. And if you look at lag versus energy, you see it's roughly log linear, pretty close to log linear. And actually, AstroSat results, for example, in recent years have pushed this up to significantly higher energies and shown that log linearity continues. And so, this log linear dependence led originally to ideas that maybe the lags were caused by Comptonization delays, because basically you have a number of scatterings. Each scattering has a multiplicative effect on the energies of the photons being upscattered. And so the result is that you get this log linear dependence of the sort of path length through the Comptonizing region on the energy. And hence you get a log linear dependence of the lag on energy. And so that was the explanation, to motivate a lot of work on Comptonization delays. For example, either a very large corona, but that has problems with sort of heating it. And so that then led to jet models for Comptonization, which Nick Kalafis will talk about shortly. And the other alternative, there's very different models, because if you invoke Comptonization delays, because the lags are really large, right? They're sort of hundredths of a second or even tenth of a second. You end up with coronae that are thousands of RG gravitational radii in scale, right? But a way to avoid that is actually if you have the lags being caused by propagation. So the idea is that you have some sort of hot accretion flow with power law emission coming from that, and maybe higher temperatures, harder power law spectra coming from smaller radii. So as you have fluctuations in the mass accretion rate that propagate inwards and drive the variability, they end up producing these lags where you have basically the softer power law first and then the harder power law as the fluctuations move inwards. So that was the sort of competing picture for those hard lags. But remember, the key point is we didn't see anything below 3 keV, so we didn't know what the disk was doing in terms of variability in these states. Now, the other important result that came out of all this phenomenology, and it really, I'm not doing justice at all to what RxTE did, it just did amazing work, and this is just a tiny, tiny subset of the things that it discovered that are relevant to the points I'm trying to make. But we clearly saw this evolution of the timing signatures. Basically, as you go through towards the state transition from the hard towards the soft, the hard intermediate, soft intermediate state, you see that the free characteristic frequencies move up to higher frequencies. And the idea was that we're seeing kind of a changing truncation radius of the accretion disk. So the accretion disk is truncated further out than in the most stable circular orbit, and you have this inner hot flow, and that hot flow is itself is unstable. And so that's why we see this variability in the power law component, which is due to the mass accretion variations in this hot accretion flow. and they propagate inwards relatively quick because it's geometrically a thick flow, and that can produce the lags potentially, but it can also, having the dynamic range here that you cover in radii, a wider range of radii means that you cover a wider range of timescales. So the shortest timescales are set by the innermost radius, and the longest timescales at the outermost. And so if you increase the radius, the truncation radius of the disk, you increase the outer radius of this hot flow, and therefore you shift the frequencies to lower frequencies. So you end up broadening the range of the power spectrum. So that was the idea that emerged, that you could perhaps, how you could explain these as this kind of varying disk truncation. One of the assumptions was that the disk isn't variable. And I think that partly came about because in the soft states, when you look at the accretion disk, when the disk dominates the emission, you just see very little variability, like 1% RMS or less. So that was the idea, that maybe it was the power law, that the hot flow was producing this variability. But we didn't see any disk emission, of course, in these particular states, because we were using RXTE, so we couldn't see down to the lower disk temperatures, 0.3 keV or something in the right hard states. Now, another key result from RXTE, which came a bit later on, I mean, there's just an incredibly rich archive of RXTE data that you can look at. And this is involving the lags and looking at the lags in the QPO. So you can see that these lags evolve with QPO frequency. They actually evolve in a complicated way. So if you measure the lag between two different bands, just as a phase lag, and then plot that versus QPO frequency for many different sources, you find that there's kind of branching out where the phase lags get larger and larger in amplitude, but different in sign as you go to higher frequencies. And it turns out that depends on the inclination of the binary orbit, which is a bit strange, right? If you're looking at a QPO, which is coming from the innermost regions, if that QPO was itself some sort of intrinsic luminosity change, you can explain this much easier in terms of changing geometry that the QPO corresponds to, for example, a precessing hot inner flow. And that's one of the sort of going models at the moment for interpreting the quasi-periodic oscillations, the low frequency kind. Now, Exelon Newton had, I think, an important impact on spectral timing because of access to soft X-rays, right? Because of this, the lower energy coverage that it had. And so even though you couldn't look at as bright sources as RXTE and observe all these really interesting state transitions, you could at least study the hard states in some detail, and we learned a lot from that. So the first thing is that it turns out that we were wrong about the disk being stable. You know, the thing that we came to conclude from the RXTE was just because we couldn't see what the disk was doing in the hard states, and it turns out it's much more variable in the hard states than it is in the soft states. And you can show this using variability spectra like the covariance spectrum. You can just do a ratio here to the power law, but what you find is slow variations at seconds have relatively large amplitudes of the disk variability compared to fast variations, which also show disk variability, but not as much as at slow variations. And so you can interpret this as there being extra source of variability. It could just be driven by heating by the power law, but there must be something extra to produce the extra amplitude of disk variability on longer timescales. And you can also see, if you look at the reflection, that the iron line here has the same amplitude on both long and short timescales. So you know that it's not variable reflection that's causing this difference, because the amplitude of the actual reflection component is the same. And so that gave the idea that the disk was intrinsically varying and perhaps even driving the variability of the power law. And I think that was more or less confirmed when we looked at the time lags, that you could look at the soft X-rays versus medium. So that means soft X-rays in this case in GX339, these are both from GX339-4 in a hard state. And the soft X-ray emission is coming from the disk predominantly. And the medium X-rays and hard X-rays are coming from the power law in two different bands. And what you see is that there's these very significant, these positive lags correspond to the hard component, the power law, lagging behind the disk by up to sort of almost up to a second actually on the longest timescales. And those are really significant lags that you can interpret in terms of propagation through the accretion disk. So the disk is driving the variability also in the power law, but with some delay. Also, interestingly, you see this negative lags, switch to negative lags at high frequencies, short timescales. So that corresponds to then the disk starting to lag behind the power law on those timescales. And I'll come to that in a minute. So how do we interpret this? Well, when you see this, if you can look at the lag versus energy now. And so what we saw when I showed you that log linear plot from the Kotov paper earlier on from Cygnus X1, similar behavior in GX339-4, that is basically this bit above 2-3 keV, right? So it's this kind of flattish part. So it's not actually, the lags aren't really that great really in the power law compared to this component at the soft X-rays, which is due to the disk. So these photons here down to sort of 0.5, 0.6 keV are leading the power law variations by at least sort of 0.3 seconds, something like that, on timescales of maybe 10 seconds or so, or tens of seconds. And that's a large lag, right? That's very large to be light travel lags. And so that's why we think that this is probably due to propagation through the disk itself, with the fluctuations then driving the thermal emission from the disk, so the low energies first, and then reaching the power law emission to produce the lag, and that you can then produce something that looks like this characteristic shape. Although it can't explain the lags within the power law itself, but I'll come on to that. Then we have at higher frequencies this signal where the disk starts to lag behind the power law. That's the so-called reverberation signal. And that's what people have been focusing on a lot recently with NICER. And that's just interpreted in terms of the heating of the disk by the power law component. And then maybe the idea is that these are light travel delays. I'm going to suggest that maybe they're not. And I'll come to that in a minute as well. So there is, looking at this with XMM Newton, there was already some evidence that things were changing with the lags, and in particular the reverberation lags as a function, for example, of accretion rate. For example, this work by Barbara DeMarco and Gabriele Ponti in 2016, where you see that the lags actually get quite large as you go to low accretion rates, for example, in H1743. And I started kind of getting quite uncomfortable with the large size of these lags, because you're seeing these lags because they're in the disk spectrum, right? But that means the disk spectrum has to have a temperature of like 0.2, 0.3 keV, but then at radii of 500 gravitational radii, which seems a bit strange if the disk is really truncated that much. So I think that was the first warning sign that we weren't seeing maybe disk truncation in these things, that we were seeing something different. The QPO, you also see with XMM Newton this modulation in the lines, in the ion line profile as well, that showed potentially evidence for precession. So this is one of the big results from XMM Newton, but I won't dwell on that because we haven't yet really got these results through from NICER yet, but they are being worked on. Okay, now NICER, I think I've got my slides out of sequence here. Let me first show you the beautiful obligatory movie. The great thing about NICER is that it's on the space station, so you can actually make movies and take photos of it. And what's nice about NICER is that you can have this fantastic flexibility of pointing. And so you have this amazing, this is just all the observations in over 2 years, to 2017 to 2019. And we were very lucky to have some very bright outbursts then, for example, Maxi J1820. And so in just 100 seconds, you can get amazing light curves with 20,000 counts a second. And then in 100 seconds, you can even get a spectrum where you can see the disk back body and the ion line, which is quite incredible, really, I think. So that's the capability of NICER, that you can really observe such bright sources and do it with CCD quality spectroscopy. The QPOs, Mariano, I think, will talk about this shortly. He mentioned that you see this in this answer to the question, that you see this interesting behavior at soft X-rays. And so that's already something that we're seeing new with NICER, is this interesting change in the behavior of the QPO at low energies. So the key thing is soft X-rays have a lot of interesting stuff going on, also in these transitional states as well, but I'll leave it to Mariano to discuss that. I'll focus a little bit at the end now on just these reverberation lags. And essentially, you know, what we see with the NICER data, because you can monitor now these changing, evolving states, and this is just in the hard state. Eventually, Maxi J1820 transitioned into a regular soft state after some time, but it spent a long time in the hard state. And then during that time, there were many observations with NICER, and they revealed this evolution of the lags. So if you look at these negative lags, which we thought was maybe reverberation signals, they change in both the frequency range they cover and also the amplitude of the lags. And the interpretation of that, because the ion line wasn't changing shape too much, is that maybe that corresponds to perhaps evolutions in the scale, not so much evolution in the truncation radius of the disk, but evolution in the height of the corona. So you could explain this with light travel delays, but with a corona with changing height. So if the corona gets higher, it's further from the disk, and therefore that increases the amplitude of the lags. And it also shifts the lags towards lower frequencies, because you tend to see sort of respond to fluctuations maybe further out in the disk as well. But there is a tension between the lags that are measured from reverberation, or that are inferred from assuming these light travel times, and the reflection measurements. The reverberation lags come out to hundreds of gravitational radii, and this is especially clear in the hard to soft state transition. where you get these lags of 0.01 seconds of the soft X-rays relative to the harder X-rays. And remember, this is a time when you see quite high frequencies in the power spectrum. So that can't be distruncation, right? You would assume. So maybe it is a height change, but it would have to be a very large change in this height. And it's not really that consistent with the reflection spectroscopy. So one of the ways that we can address this is by considering the other components that are where the disk and corona are interacting. So far, we've just been considering this heating of the disk by the corona. So the stuff propagates through the disk and reaches the corona, and then you get these hard lags. And then also the heating of by the corona of the disk, which produces soft lags. But we should also think about the seed photons that go into the corona, and they actually change the photon index and change the shape of the corona. And those seed photons cause the corona to respond to fluctuations in mass accretion rate before those fluctuations actually reach the corona and heat it. So you get cooling and then heating, and therefore changes in the spectrum and time delays result from that. And it turns out that if you model this, and if you're interested, just go to this poster. This is some work I've been doing with Julian Malzak, and we're hopefully about to submit it in the next few weeks, the full paper. But look for that poster for a preview. And basically, if you put these effects in and model this with mass accretion fluctuations going inwards, you actually end up with something that looks very similar to the data, where you have these soft power law lagging behind the disk at low frequencies, and then switching to these negative lags. And this can be entirely explained with the seed photons, because basically the reverberation is actually lagging behind the seed photon component, and that actually produces these negative lags. And you know, you can get these quite large lags even when the corona is quite compact, just you know, below 10 gravitational radii. So I think actually maybe we're misinterpreting those lags, and they're not light travel times. They're actually associated with propagation and with the effect of seed photons on the corona. So the key point for our XTE is that the light travel delays are probably found at higher frequencies, because if you go back actually to the frequency range where you see these soft lags, you can see that they go to 0 at tens of hertz, right above maybe 50 up to 100 hertz. So we need to go to 100 hertz, I think, to see the real light travel time lags, which should be there because we think reverberation is there. And so the things that we simulated with EXTP were at these high frequencies. Fortunately, I kind of maybe did it to be conservative, but that we should definitely detect these light travel time signals with EXTP if they're there. Well, they should be there really, otherwise something's very wrong with our understanding. And it's also important that we've really got to consider soft X-rays, right? So we've seen that there's all kinds of interesting things going on in soft X-rays. We kind of ignored them for a long time, mainly because, for example, high frequency QPOs, we still don't see really in NICER data, and QPOs tend to have relatively hard spectra. But when you go into soft X-rays, you see lots of interesting behavior, and I think they're crucial to really understand the role of the variability of the disk and its seed photons. And if we don't understand that, I don't think we can interpret the timing very well, the rest of the spectral timing we see it in harder X-rays. So I think EXTP is going to be really crucial for this because of its wide spectral coverage as well as its large collecting area. The other important point is that all the current models, I think, are too simplistic. That's including mine. We really have to do some serious work to improve them, and especially involving the GRMHD community. So I'm looking forward to Jibbo Masoko's talk later on, you know, because the GRMHD work, I think, is starting to converge towards the kind of you know, timescales and dynamic range that we need to start comparing with data. So I'll stop there. Thank you.
All right, thank you, Phil. I think we're gonna a little bit over time, but it was such a nice, also giving some introductory information about the XTP that I didn't want to stop, but we have maybe not too much time for question. Javier has a question. If the density in the disk changes, that can produce changes in the soft flux, but not at the iron line. So could that explain the apparent disk variability?
Maybe, but then you'd have to have changes in the disk density, but they weren't connected to mass accretion changes. So it kind of seems like maybe both of them could happen, right? That you could have both changes in disk density, but then there'd be mass accretion changes at the same time, because these still have to precede the variations in the power law emission. So there still has to be some sort of causal connection, whether it's just fluctuations of a surface layer of the disk or not. But if you look at the luminosity coming out, right, it's the amplitude of variability of the disk emission, the black body emission, is tens of percent. It's larger than the power law emission, actually. So yeah, I don't really know how you can do that without really affecting the core, you know, the region where most of the viscous dissipation is happening in the midplane of the disk.
Yeah. So Phil, this was very interesting what you're saying about the effect of the seed photons causing some of the structure that we're seeing here. Did you consider the possibility that there might be synchrotron seed photons from the inner hot flow itself? And if so, and maybe this is a little bit of an open-ended question, but maybe if you just say whatever you feel like about that topic.
Yeah, you can put them in. So it's a generic thing with the seed photons. So you can have them local in the hot flow, and what they then do is they just reduce the lags. So the power law lags that you see, I didn't mention this, but the power law lags within the power law emission, those log linear lags, they can be produced, they can be explained by the seed photons, just the fact that you have this cooling then heating. And if you put the seed photons locally, then you just reduce that lag, because the lag is there because of the time delay between stuff going through the disk and then heating happening in the corona. Right. Because the seed photons.
So potentially, if we could measure lags in quiescence, they might start to get short again because synchrotron might be more important then.
Yeah. And it's also worth pointing out neutron stars have much smaller lags for the same states, which is consistent with them getting their seed photons from the boundary layer and not the disk.
Yeah. Okay. Good point. Yeah. Thank you.
Thank you, Tom. I have one quick question. So your latest model, I mean, does it say anything about truncation at all?
You can have truncation of the disk in there as well, and that just changes the lags. But if you look at varying truncation radius, what happens is the spectrum gets harder and then the lags get larger, but we tend to see the opposite effect, that the spectrum gets softer and the lags get larger. So it doesn't seem that the data are telling us that truncation is happening much, at least in the bright hard states. The caveat is we haven't looked at the fainter hard states where truncation could indeed be happening.
All right, thank you very much. And I think we should move on to our next speaker.
Okay.
So Nick,